So I'm going to talk about probably the culmination of about 35 years of attempts to find something better than floating point arithmetic, starting in the 80s, I think is when I started working on this. Right now I'm expatriated to the University of Singapore, and they've provided a very good home for me to work on this kind of research, and I appreciate that. So why worry about floating point? I came up with a simple example because I found out that everybody trusts matrix multiplication. They use it for examples all the time. Well, suppose just one row and one column happened to be this A and that B. So you were taking their scalar product in order to find out the result. And these are fairly ordinary numbers. These are integers. They're not that big. 32 million, 1, -1, 80 million, 40 million. No, perfectly ordinary, reasonable numbers. If you do this in single precision, you'll get A dot B equals 0, which would tell you, hey, these vectors are orthogonal. Might be an important property to know. Check it by doing double precision, and you again get A dot B equals 0. And you know what's coming. Let's suppose you do it with a binary sum collapse, where you don't do it from left to right, but you do it these two, and then add them, which often helps the behavior a little bit. You get 1. And those two numbers are about as far apart as you can get in terms of meaning and accuracy. The correct answer is actually 2. So most linear algebra is unstable with floats. I'm always amused when I hear people talking about like this method is stable, but this method is not. Actually, they're all unstable. All of them can be made very sensitive to tiny changes in the input. Floating point is as dangerous as all get out. It is just nothing but a swamp. And yet we get along with it just fine because we're so used to it. We've suffered under it, and we've just said, well, you got to learn to live with it. First of all, my main objection with IEEE 754, the standard from 1985, is that it's not a standard. It's a guideline. It has a section of requirements. It has a section of suggestions, recommendations. Well, people take those or don't take those. As soon as that happens, you're going to get different binary output from every different computer system. Actually, the way that the standard is set up, you can get 2 different answers from the same computer running the same operating system, just doing it a few seconds apart. There isn't even consistency from one run to another because it's affected by cache. Whether you took something out of the 8087 stack and put it in the cache temporarily and then put it back, suddenly you got an overflow in one case, but you got a nice reasonable number in the other. That lack of guarantee is just crippling. If you're trying to debug a system and you're getting different answers on different systems, the whole idea of a standard is that you get the same answer on every system. The people who conceived of Java, I remember James Gosling was just horrified when he discovered that using IEEE 754 was no guarantee of identical results across all platforms in Java. When you make mistakes in rounding errors, of course, it's completely quiet. They put in something called the inexact flag, which every processor designer has to make sure is maintained. So if you get an inexact or rounded result, the flag goes on inside the processor. Have you ever seen a language that lets you see that flag? In fact, the only way you're going to see that flag is probably by getting into the assembler and being very, very good with a debugger and being able to reset the processor flag, do an operation, then check the processor flag again. It's never been made mainstream. And of course, it breaks the algebra laws like associative arithmetic. A plus grouped B plus C is not the same as grouping A plus B and then adding C. And that means that compilers are not free to rearrange numbers without changing the answer. But they do anyway, of course. So the distributive law also does not hold. There was even once a machine that didn't have the commutative law satisfied. A times B was not equal to B times A. That was the Cray 1. Incredible. That was a real headache. They finally fixed it by always sorting it so that A was less than B. So you got the same wrong answer every time, and people weren't happy. Anyway, it overflows to infinity. If you get too big of a number, bigger than you can represent, what does floating point do? It says, well, let's just use infinity instead. How stupid can you be? Which is closer to a big number, infinity or 10 to the 38th or whatever your number is? I found out why this happens from that man right there, Dick Seitz. He explained it to me when he was visiting in Singapore. The rule is round to nearest even. Well, infinity is an even number and 0 is an even number in terms of, round to that one. Well, think about what you're doing because that makes the answer infinitely far away on a logarithmic scale. There's no way to express most of the real number line if you think about it. All you can do is pick little rational numbers and say everything's going to be close to one of these. But most of the real number line is not n times 2 to the minus whatever. So the key idea I came up with a few years ago was to put a bit on the end of the number, right at the end of the fraction, that says, is it exact or not? You see, we've always had a way of expressing infinite precision infinite decimal real numbers with a finite set of symbols. We've been doing it for a long time. If you want to say pi equals 3.14, that's wrong. But if you just simply write pi equals 3.14 ... after it, you mean there's more decimals after that. That means it's between 3.14 and 3.15. It's not equal to either one. If it was equal to 3.14, you wouldn't have needed the ... If it was an infinite set of 9s, let's say, after the 3.14, that's the same as 3.15, and you would have said that. So all you need is the ... or the absence of a ... to mean there's more decimals after this. Well, that's the open interval in between exact intervals, and it's 1 bit. So just like you put a sign bit in front of a number to say whether it's positive or negative, you put a U bit after the number to indicate whether it's exact or in between exacts. And that's a very powerful idea that lets you get some of the trappings of interval arithmetic and valid methods without having to have a pair of numbers in order to represent everything. Let's go back to IEEE 754, because I'm not done haranguing about it. The exponents are usually too large. And if you've built floating point hardware, you know that it's easier to build an exponent than it is to build for the fraction. I think this was really one of the big reasons. So these exponent sizes were decided by committee back in the 80s. People saying, I want a 16-bit exponent, I want an 11-bit exponent. And it was largely on what was easiest to design, not what people were actually using. We've done some studies at Lawrence Livermore that indicate that almost never do real application codes go much outside of 10 to the 13th to 10 to the minus 13th. And yet we've got hundreds of orders of magnitude supported by the IEEE standard. So the accuracy is fairly flat. Of course, I'll show you the pictures of the wobbling accuracy of floating point. It's fairly flat across a vast range, and then it falls off a cliff. And there's probably a better way to manage accuracy. There's a lot of wasted bit patterns. You've got both 0 and -0. That means if you want to check if x equals to y, you can't just look at the bits. You have to say, well, if it's 0, then check the first bit. You can imagine that, complicating just to check to see if two things are equal. And there's like 5 quintillion different ways to represent nan in double precision, not a number. I don't think we need those. There's a lot of other things we could do with those bit patterns. Subnormal numbers are a headache. Well, the Berkeley people have come up with a fairly clever way of adding a bit to the architecture so that you don't have to suffer quite so much with subnormal numbers. Mostly, it just adds a whole lot of transistors and space to your chip. And you know, the benefits are limited for most people. Divides are always hard. They're much harder than for multiplication. And decimal floats, while they're part of the standard, there is no 32-bit decimal float. It goes 64 and 128, I think, are the only sizes for decimal. So here's a quick introduction to the Unum format that I introduced in 2015. I call it type 1 because there's some variations, and the second variation is so different. It preserves the idea of an uncertainty bit. But what I was trying to do is doing the most gradual thing imaginable. I'd take the IEEE standard and add 3 metafields to it. So you got the sign, exponent, and fraction for IEEE. And this happens to be a half precision float, which is 5 bits of exponent and 10 bits of fraction. And that was pioneered by NVIDIA and I think Lucasfilms. They wanted something that they could store some of their video information. And it had just barely enough dynamic range and enough precision that it wouldn't lose all the goodies out of the movies. But now it's being supported in hardware. NVIDIA started supporting native 16-bit half precision floats. And Intel's made the transition from just supporting the format to actually doing the operations with only 16 bits. So these are starting to come in vogue because they look like they're good for neural networks. And that's all the precision you need to train a neural net. So I wanted to be upward compatible by adding the U bit on the end and then a field that says how many bits of exponent do you have and how many bits of fraction do you have. And of course I have to set the size of that field, but in this case like a 3-bit exponent size and a 4-bit fraction size suffice to give me a big range of sizes. And this means that you track the amount of uncertainty, because where the uncertainty bit falls will tell you how much range there is. If it's in a very low precision, a low order bit, then you'll know it's a very approximate number. If it's way off to the right, then you know you have a precise number. And if anybody wants to know more about this, I'm not going to talk about it much tonight, but this is the reference that I have at the bottom of the screen. They keep running out of this at Amazon. I see that they're down to 4 copies. It's in its 3rd printing. And it was briefly in the number 1 bestseller, which sounds good until you realize that's in the category of number systems. But there's 4,000 books in number systems. Okay, so it's something. Here's one graphical way to imagine floats. as discrete points on the real number line. And here I've got a 5-bit float that still follows IEEE rules, believe it or not. You can really push these things down if you are careful. I think I got it all the way down to 4 once. But there's the sign bit, which is all 0 for the positive numbers, and 1, the red 1 for the negative numbers. And the hollow dots you can see up there are the subnormal numbers, denormalized numbers. They actually fall below the smallest exponential type number. But anything which has 2 1s for the exponent, in other words, the exponent's completely full, the first one is infinity, and everything else is NAND cases. So this is what you can represent with a 5-bit float. And you can see it goes like 0, 1/4, 1/2, 3/4, 1, 1 3/4, to finally gets up to 3 1/2. The next number represents infinity, and then after that it's not a number, not a number, not a number. Kind of wasteful. So what happens if you use my system with the U-bit is you can represent the exact values or the range between exact values, and that includes at the very last step between 4 and infinity. So this is exactly 0, between 0 and 1/2, exactly 1/2, and so on. So that system allows you to cover the entire extended real number line with very low precision. But if you ask, what is the square root of 2 on this, I'd say, well, that's between 1 and 1 1/2. It's that open interval. And you can calculate with that, and you can say mathematically correct things without making true misstatements about the value of a number. The risk of all of these types of systems is that the intervals that you're bounding things with tend to grow. And that's why interval arithmetic and any kind of bounded arithmetic is tricky to use and has not caught on. It was invented in the late 50s by a Stanford man, I think. It was Ray Moore. And has been pioneered by several Stanford people ever since then. But it's always been kind of a cult following for interval arithmetic because it's tricky to use. And one of the reasons I did this is to try to make it easier to use. So type 2 unums, something I had a flash about a year ago, which is instead of using the real number line from negative infinity to infinity, use the projective reals, which meet at the top at plus or minus infinity. So imagine projecting a light at the top, and it will cast a shadow on the real number line. Okay, so plus at the very top, it go either plus infinity or minus infinity. So you can define these points within certain parameters, but 1 always goes over on the east, and -1 always goes directly on the west. But the numbers you put in between, you have a lot of flexibility, which means you can do a custom number system. But one of the key ideas is that it has perfect reciprocation. If x is here, its mirror image 1 over x is down here, which means you now have multiply and divide on equal basis. The same way that add and subtract are equally easy, you just reflect. Because you can negate something with a unary minus, now you can reciprocate something with a unary slash, and it works perfectly. So there's some beautiful advantages for this, and here I've shown you that I can do it with the decimal lattice. What's the catch? Well, I don't really have circuitry that does this. It's very tricky circuitry if you're trying to do it with things like shifts and integer operations. So I have to resort to table lookup. And table lookup looks really good up to a certain precision, because table lookup could be incredibly fast. These are not numbers, these are pointers to numbers. And so you can manipulate pointers much faster than you can manipulate the numbers, up to the point where you run out of memory, of course. But I suspect we can get a lot of ROM onto chips, so I still hope somebody does these, at least up to like 20-bit precision. I wrestled with this for years thinking, if only we didn't have to use table lookup, if there was some better way to do it. Well, let me contrast 2 calculation aesthetics, because there's a lot of people out there talking about approximate computing as a thing that's going to save us and get us to exascale, which means make computing even worse than floating point so that it can go faster and use less power and make a lot of mistakes and maybe be good enough. And they've explored to see what kinds of applications are so tolerant of lousy computing that you can get away with that trade-off. Well, I think what they're really reacting to is the fact that with IEEE Standard, they did something that was fast and good enough, and yeah, it left out some stuff. And then they started throwing in some rigor, just a little bit of rigor. Let's give them multiple rounding modes so they can play with different rounding modes. Let's give them subnormal numbers so they can more smoothly go to zero. They did all kinds of things to try to improve the quality and get more verifiability. Well, you can't do that just a little bit, or else you get nothing, right? It's not completely mathematical provable. It still makes all the mistakes with not following the laws of algebra. Then there's the people who want absolute rigor, the people who do interval arithmetic, or they use Unum arithmetic, the way I like to see it used. sets of real numbers can be actually represented very precisely, and you can manipulate them as well as you would do like with Mathematica or Maple, but actually still be doing arithmetic. But that's a whole different aesthetic. And as I say, there's a lot fewer people that are interested in that kind of absolute perfection, unless you're designing a nuclear power plant or trying to figure out how to land the space shuttle. Maybe people don't particularly need that kind of a special care. They just want something that's fast enough most of the time and it works, especially if you're playing video games. Let's face it, you don't really care if you lose a pixel here and there when you're playing a video game. But the thing is, if you mix those two aesthetics, which is what we do right now with IEEE floats, you get neither. It's not as fast as it could be because it's got all this garbage in it to try to help you out. And it's not rigorous because, well, it isn't. You got to go all the way to one or all the way to the other. So instead of doing approximate computing, I think we should do floating points aesthetic, but do it right for the first time. So I call these things posits. And a posit, I looked it up, is a statement that is made on the assumption that it will prove to be true in philosophy. And that's a more polite word than guess, as I was calling these things guesses, and William Kahn got angry at me for doing that. So I'm calling them posits now. It's a little softer word. But let's face it, it's not a provable number. You say, I think this is the right number, and I'm going to work with it. It's just like you would introduce something philosophically. So here's some metrics for number systems. I've seen a lot of papers saying, here's a great number system. It uses all logarithms. Or here's one that uses all rational numbers. Isn't that cool? But I never see them say, what are your metrics for comparing one number system against another? And there's a lot of things we could use. So most of this talk is going to be about what the metrics are for comparing two number systems. Well, there's accuracy. I've got a kind of a funny looking formula there. You might think accuracy is, well, like relative difference. So how far apart are they divided by their size or something like that. But on a logarithmic scale, if you think about that, it's actually the log of one minus the log of the other, which is the log of the ratio. And how many decimals it is, well, you got to take another log. So if you work it out, negative log base 10 of the log of the base 10 of the ratio of two numbers is the number of decimals of accuracy of two closely spaced numbers. So as I tile the system with numbers, that's what's going to be my accuracy plot. Dynamic range is easy. It's the ratio of the biggest number to the smallest positive real number. And if you take the log base 10, you get how many decades there are in your system. And you'd like it to be symmetric, about 1, but it isn't always that way. What percentage of operations are exact? How often do you, let's say, add two numbers and you land exactly on another number in your system instead of having to round? It'd be nice if that happened a lot, because maybe you could do perfect computations for a fairly large fraction of the time. But when they aren't exact, how much did you lose? How many decimals did you have to round it by in order to get to the answer that you could represent? And we can compile all of those, and then we can do like histograms or scatter plots or whatever, and compare two different number systems. Think about the entropy per bit. If you had, I'm imagining a bunch of LEDs that are all the bits of a 64-bit number, and they're flashing like crazy as they represent every single floating point number in a computer as it goes by. I'll bet you those exponent bits aren't moving very much. There's a whole bunch of them that are just sitting still all the time, because you almost never use 10 to the 300th power, let's face it. And so the high order bits of those are mostly wasted. So they didn't think about trying to maximize the meaning of every bit when they designed these things. And finally, I think the real proof of the pudding is to come up with some benchmarks, like evaluate this formula, solve a system of equations, do an FFT, do the inverse FFT, see how close it came to coming back to the same thing, do basic math library kernels, and find out how accurate this system is versus another system. And the main cheat you have to watch out for is people can turn up their accuracy by turning down their dynamic range, right? You take more bits from the fraction, from the exponent and give it to the fraction. Well, let's see if we can do better than we do with floats without having to do that. So here is a diagram of a Posit arithmetic format. And you notice that the only thing that's got a solid vertical line is the sign bit. The others, the division will vary. The regime bits is the run of bits that you have at the beginning. Like if you have 1, 1, 1, 1, 0, that would be 4 represented by 4 ones and then terminated by a 0. If it was 0, 0, 0, 1, that would be -3. It's a lot like extra, extra large, extra, extra, extra large. I just bought it, just before I got here, I went to Orchard Supply Hardware and got some steel wool, and I was buying 000 steel wool. There was 00 steel wool, and there was quadruple zero steel. Okay, the number of zeros, it keeps getting finer and finer. It's like women's sizes, same thing. So that's how the regime bits are defined. The exponent bits, if there are any, are simply a positive, an unsigned integer. There's no bias. Floating point has to have this funny looking bias that you have. And then there's the fraction bits, which are always a normalized, that is, there's always a hidden bit. So this works like floating point, except for that funny stuff in the beginning. And I'll show you where that comes from. I didn't use the U bit because I'd much rather, if I'm going to round every time, I'd much rather have that last bit for the fraction and get a little bit more accuracy. It will round after every operation, but if you get too big of a number, it will round down to the largest representable number, not up to infinity. So it doesn't make that mistake. The ES is sort of the equivalent of the adjustable exponent size. And you can have an exponent size of 0, not have one at all, or 1 or 2. But you'll see that a small number of exponent bits gives you a very large dynamic range.
You actually have, though, another vertical line there, and that's the end, and you haven't said anything about...
Okay, yeah.
Old terms, signal precision...
Yeah, I'm assuming people will pick a size, and it will be 16-bit, 32-bit, 64-bit, and that will be the standard. These are things that are capable of being anything from 3 bits wide to thousands. But I suspect the hardware is not going to allow that flexibility. I have yet to meet a hardware engineer that's willing to let everything be floatable at runtime, both the exponent size and the word size. So I understand that. So I assume that I'm going to be beating floats at their own game. 16-bit versus 16-bit, 32-bit versus 32-bit. Let's duke it out, okay?
Maybe I should also bring up, these numbers are isomorphic, so the pattern doesn't change. So if you, except for the ES, so if you fix the ES, if you do a 16-bit number and a 64-bit number, the beginning parts look the same. So you take a 16-bit number and extend it with zeros, it'll be the same value in 64 bits.
That's the amazing thing, is that adding bits to the right actually increases both the accuracy and it also increases the dynamic range, which is kind of mind-blowing. How can that possibly be? You think like fractions, it works that way, but it doesn't work with dynamic range. Here's an example, just to see how it would work. Here's a sign bit is 0, so that's a positive number, same as floats. Regime bits 0, 0, 1. In this case, the UC, which is 2 to the 2 to the third, or 256, is, there's 3 regime bits terminated by a 1, so that's 256 to the minus third power. Then you multiply that by the exponent bits, which represents the number 5, 1, 0, 1. So it just scales it by 5. And now you finally got the scale factor. So it's a floating point number in the sense that it's a power of 2 times an integer. But the integer in this case is 221 over 256 with the hidden bit. And I think that if you can build a float out of conventional circuitry, then it should be very simple to build this as well. And it's going to be simpler because I'm going to strip out a whole lot of the exceptions that you have to wrestle with IEEE. And they don't overflow and they don't underflow, so you certainly don't need those flags. And there is no NaN representation. It's not a number, right? Why are you assigning a number to something that's not a number? It's fundamentally illogical. If you are computing something and you get a nonsense operation like 0 divided by 0, the right thing to do is stop and report it, or interrupt and let the interrupt handler say, I don't mind, substitute this and go on. Whatever it is, you don't keep wasting energy and time by computing something at this point where you've got garbage. You report it back to the user and let them do something about it. So if you take out the NaN, wow, does that simplify a lot of stuff. So this should be simpler, smaller, and faster circuits than IEEE 754. Let's go back to that projective real number line, because I want to show what Isaac was just mentioning about how you just add bits and you can increase something. I'll pick a U seed of 4, which means the exponent size is 1. So 2 to the 2 to the 1 is 4. And you'll see why these work out so elegantly. Now, that looks a lot like type 2 unums in that I've got perfect reciprocation. And you will always get perfect reciprocation for powers of 2. Also, 0 is exactly 1 over plus or minus infinity and backwards. So those work out just great. You just take the 2's complement of everything but the first bit in order to take the reciprocal. Yeah, if you have something on the left-hand side and you say, well, that's a negative 2's complement number, so flip it over. Notice that what you're representing will be negative, but flip it over, and then I'll be talking about the pattern of bits from that you get on the positive right-hand side. So if you're inserting a number between, let's say, the 4 and the infinity, you factor another factor of 4. So now it's up by 16, 4 times bigger. Down at the bottom, if you're between 1/4 and 0, it's 1/16. So if anytime you're interpolating between infinity and your biggest number, you multiply it by the u seed. So it keeps on getting bigger and bigger as you get, like the doomsday clock, very, very close to midnight. And if you're between, let's say 16 and 2, well, you can put a power of 2 in there. So that means I'm going to be adding, well, let's see. I already did that one. Between 4 and 1, now that's more than one u seed factor, but it's a power of 2. So I can put a power of 2 in there, which means now we're looking at exponent bits, and the exponent bits are showing up in blue here. So I've got gold regime bits followed by blue exponent bits, and that's the rule for doing this as a recursive thing. When you finally actually get something like between 1 and 2, the only thing you can do is now interpolate it linearly. So 3/2 goes between 1 and 2, and 3 goes between 2 and 4, and you see the fraction bit shows up in black at the end. And I know this all sounds very complicated, but it really is nothing more than floating point that takes into account whether you're doing geometric increases or linear increases automatically. So if you round a number, let's say between 4 and 16, I give you 12, well, it would use the geometric mean as with the number that goes in there instead of the arithmetic mean. So that's actually a better way of rounding, but you don't have to do any special hardware. It's just the same thing as you would round normally, except don't round to infinity and don't round to 0. But the cool thing is, as you add bits, you add a 0 to something, it doesn't change it. If you add a 1, so it's in between 2, then you get this extra accuracy, and you get more dynamic range at the north and the south. It gets bigger and smaller, and on the right and the left, it gets more accuracy. There's something fundamentally logical about this. It just looks right to me, as opposed to being cobbled together. So here's a metrics-based study, and I'm going to pick a number. I have to wrestle between doing a realistically large number and doing one where I can do every single possible case and study it. If I have an 8-bit float or an 8-bit posit, then the addition table is going to have 65,536 entries, because I've got 256 by 256 possibilities. And I can study the errors of every one of those, and I can show them to you on the screen. So that's where I picked, let's say, a quarter precision IEEE float. Not that there really is such a thing in the official standard as a quarter precision float. Maybe there should be. But sign bit, 4 exponent bits, and 3 fraction bits seems to be kind of true to the aesthetic. And it's got a dynamic range of 5 orders of magnitude. And 2 ways to represent 0, unfortunately, and 14 ways to say not a number. Here's what the float accuracy looks like. If you plot it, it has tapered accuracy in that off on the left, you see it tapers down to 0. Now over on the right, it had gradual underflow, in other words, but it doesn't have gradual overflow. That's where all the nans are. They missed a trick when the committee met. They didn't realize that all this stuff about tapering towards 0 has a perfect analog on the other side that they could have used. They could have had tapered accuracy on the other side as well. So remember these numbers, average is 1.4 decimals of accuracy, and maximum is 1.55. And I'll show you what posits look like. There's posits. Maximum is 1.86 decimals, same 8 bits. But there are 7 orders of magnitude expressible. It's much wider. It doesn't seem like this is possible, but yes, you can be both wider and higher at the same time. Let me put both graphs on top of each other. And you see there's a couple places where the floats actually exceed. They stick out a little bit. By the way, we're distributing all these slides. Those people who are taking pictures of the slides, I think we can get you a copy if you want. Probably much better resolution than your camera. But
Dennis asks you to put your slide. Give them to him, and you'll.
He already has them. I mailed them to him yesterday.
Right. Then they'll be on the website.
Great. So you can see that over on the right, I can express numbers that the floats can't. And for the very small numbers, possibly floats do a little bit better. But most of your calculations are in the vicinity of the unity ratios. So that's where most calculations occur. And I noticed that computational scientists everywhere scale their problems. They don't always work with, let's say, Avogadro's number or Planck's constant, so everything is 10 to the minus 34th. They scale things through so things are back in the range of understandable numbers. So I think we're ready for round 1. Round 1, unary operations. We're going to take reciprocals, square root of x, x squared, log base 2 of x, and 2 to the x. All one input, one output. And how well do we do? Well, here's reciprocation. The floats make a bunch of errors. On there's 256 possibilities, and I found out whatever the error is and sorted it from smallest to largest. I did the same thing for the posits. You notice that the posit curve in magenta is always underneath the float curve. It's always better. And in the right-hand side, it's much better because the errors that are made by floats are infinitely large. Floats get 13% exact, and posits get almost 19% exact results. So already, it goes a little farther before the magenta leaves the x-axis at all. And of course, there's no overflow, and there's no nan. I mean, even 1 over 0 turns into plus or minus infinity, and that's a perfectly closed operation. So there are no exceptions to reciprocation. So that's already looking a lot better behaved than floats. What about the square root? Only slightly more exact, 7.8% exact versus 7.03. But the real story is that curve of what is the error. When you do make an error, how bad is it? And you can see that the cumulative error going from left to right is much lower for the posits than it is for the floats. I think it gets really spectacular for x squared. Look at that. It's not only 15% exact versus 13% exact, but when floats get it wrong, they really get it wrong. Whereas this dynamic precision, where it's tapering, will try to accommodate very large and very small numbers, and will do a much better job of doing something right with those numbers and not getting it just totally giving up. And once again, they've got, look at that, 12.5% underflow and 25% overflow. That's a lot of cases to be throwing away when you're just squaring a number. This is one of the reasons that people have libraries for even doing like complex arithmetic. If you take a times b minus b times c just to do complex arithmetic, people are paranoid that they're going to get overflow or underflow when they take a times d. And that costs a lot of time in a math library trying to fix that. Here's the closure under the log. And once again, posits are more frequently exact. Log base 2, of course, is not maybe the most common thing you'd ask for, but you can derive natural log and log base 10 simply by multiplying that by a constant. So all the math libraries for all the different kinds of logarithms usually start by computing the log base 2, and then they scale it.
Why is, you're always saying that the exact is more for posits than for floats, but the inexact is always greater also. Why is that?
You say the inexact is greater? Mostly it's taking it away from the nans and the exceptions. So instead of saying, oh, I give up, it's overflow or it's underflow, I will give you an answer, and so I'll get more inexacts as well as more exacts, and then it didn't throw a gutter ball and say, I give up. That's what happens with floats, is they give up on too many of the numbers, and they don't give an answer at all.
Where do the nans come from?
Let's see, in the log, it's all the negative numbers.
And why isn't it 50%?
Okay, so you get certainly if you try to take the log of plus or minus infinity, that's going to be a nan. And in my case, log of 0 is not representable because I don't have minus infinity all by itself. So I call that a nan. I stop. I can do the interval right next to 0, but I can't do exactly 0. It would be a lie to say it's plus or minus infinity. I get big mistakes if I then exponentiated it. So I think that's the simplest explanation. Here's 2 to the x, which is, making numbers very big, very fast. It's kind of funny that it still doesn't give up and round up to infinity, even though it's a huge number. If I take the biggest number to the power of the biggest number, that's awfully big. But it still says, no, round it down. Well, it's better than rounding to infinity, but I just lost 1,233 decimals of precision. But that's better than infinity. So that works out pretty well. Okay, ready for round 2. Now here's the fun part, because now we're finally going to do arithmetic, plus, minus, times, divide. Of course, we don't need minus, that's perfect. But times and divide are definitely a little bit different, so I'll do those separately. I'm going to show you kind of an eye-popping diagram, because what I do is what I call a closure plot. I'm going to color code what happens so you can see the entire set of 64K values at once. So just brace yourself, because black means exact, magenta means an error, blue is underflow, red is overflow, and yellow means not a number, indeterminate. That's what addition looks like with floating point arithmetic. So you can see the little, kind of the little bevel down there in the lower left and the upper right where it overflows. You can't underflow with addition. You can underflow with a lot of things, but not addition. So that doesn't happen. So there's no blue here, but it's kind of a pretty pattern. The stripe from upper left to bottom right is really subtractions, because you can't see it because it's so small, but the smallest real is on the bottom left, 0, max real. And negative max real, 0 to positive max real. So you're taking differences along that diagonal, and you're taking sums along this diagonal. And it's more likely you're going to wind up with a small number that you can represent if you take a subtraction. But you see 70% are inexact, 18.5% are exact. You ready for the posit diagram? I'll go back and forth between them so you can compare them, but try to remember this diagram. I'll show you what it looks like for posits. Okay. Well, just about all the nans went away. So did all the overflows and all the underflows. There wasn't any underflow, but you see what I'm saying? Here's what it was, and there's what it is with posits. There is a nan. You'll never find it. It's right here. That little yellow dot. That's where you add plus or minus infinity to itself. That's the only thing that causes an interrupt and says, I can't go any further. I don't know what that is. So 25% of the cases are exact. Now, if you have ever tried to design a dynamic number system that has a lot of orders of magnitude, addition is the hard part. Multiplication is easy to get closure, right? Because you're scaling over an exponential series, and it's just natural to make that work. But trying to get the adds closed is really, really the trick. And I think I've got something that's considerably better than with floats here. If I sort all 64K losses from left to right and graph them, you can see posits win uniformly everywhere. And they don't go to infinity, of course. The maximum addition loss of accuracy you get is 0.3 decimals. That's the worst thing that can happen to you. That's where you add the maximum real to itself. You get twice the maximum real, and you round it back down. So you're off by a factor of 2, which is 0.3 decimal. All right, let's try multiplication. And multiplication plots, no matter how many bits of precision you use, all have these big corners cut off, because that's where they overflow. And they also have a diamond in the middle where it underflows. It's not a perfect diamond because gradual underflow. So that's a little bit rounded in. You can accommodate some of those numbers. But this is where floats finally beat me. For the first time, they got 22.2% exact numbers. I only got 18%. But look at the cost. Look at all those overflows and underflows. It's knocking out almost 1/4 of the cases. You're going to get garbage. Whereas posits just don't give up. They return an answer, and it's a meaningful answer with a lot of decimals. So I'm willing to pay a slight price in the number of exacts for getting that kind of closure in general. Now, that's the sorted losses, and actually, posits are much more robust than floats at retaining information throughout a calculation and not going completely off the rails. So the division plot, it looks a little bit like a permutation of the multiplication plot. There's a little bit of asymmetry you see there because, I mean, obviously, x over y, it doesn't have a corresponding y over x symmetry you have with commutative multiplication. But you get plenty of nan values here. Always forms that yellow frame around the float diagrams. And you get to do some slight asymmetries. Here's what it looks like for posits. And I didn't think it would show up on this screen, but it's almost symmetric. You see the little yellow dot in the center? Yeah, that's 0 divided by 0. That's the only thing that stops you. So in very tiny fraction of the cases, you do get a nan from 0 divided by 0. Other than that, it just keeps going.
Can you go back?
Yeah. Let's go see it. Whoop.
There seems to be diagonal symmetry. Is it actually there?
There's a diagonal symmetry, yes, because that's about whether you change the sign, right? Plus over plus is the same as minus over minus. But other than that, it's you don't have symmetry about reciprocation about 1. So it's if you get the actual PDF of this talk, it's kind of fun to really stare at this very up close. It's like I say, it's kind of an eye-popping chart. But I believe having the hidden bit equal to 1 all the time is going to simplify your hardware. It's just always 1. That's really nice. It's like the old days when they didn't have subnormal numbers to deal with. And most hardware engineers really like that situation. So finally, round 3. Higher precision operations. Let's take these things out for a spin, see what they can do. Now, I made up at least one very simple formula. Evaluate this formula. And tried it out on 32 bits. So I could say, if you had a budget of 32-bit values, you couldn't cheat and use a pair of them. You have to always stick to 32-bit values. How well can you do to evaluate that expression up there? See that 27 tenths minus e over pi minus the sum of root 2 plus root 3, all to the power of 67 over 16. Just a made-up formula. I made it up to be a little bit mean because obviously 27 over 10 is kind of close to 2.71828. So I just know I'm going to scrape off a couple decimals right away. And a lot of people don't know it, but root 2 plus root 3 is really close to pi. You can figure out that by inscribing a hexagon, superscribing an octagon, it works out. Root 2 plus root 3 is 3.14 and then some. So I'm going to scrape off 3 decimals in the denominator. Like I say, I'm feeling mean because I know what that's going to do to floating point. And it's going to do it to me too, actually, if I try to do it with posits. You take it to the 67 over 16th power just to make sure you know how to take powers. And taking things to powers tends to inflate errors as well. So I guess we shouldn't be too surprised that an IEEE 32-bit float on the top line, which nominally has 7.4 decimals of accuracy, although it wobbles a little, only gets 3 decimals right. And of course, you don't know how many decimals you've got right. It reported all these decimals, but only the 302 is right. After that, it's off in the weeds. So the error is 0.0297. Now, if you're going to do interval arithmetic, to be fair, that's a pair of 16-bit numbers, right? You don't get two 32-bit numbers. You get a pair of 16-bit numbers to fit in there. That's your budget. And look at that answer. Oh, my God. This is why people don't use interval arithmetic. It's somewhere between 18 and 33,000. Usually you get something like it's between minus infinity and infinity. This is actually a pretty good answer for interval arithmetic. And that's the last time people use interval arithmetic. They try it once. They said, that's fine. I'm going to go back to using floats. But that's a very big range of 3.3 times 10 to the 4th. Now, type 1 unums, I think, are still unrivaled in terms of their efficiency at representing an interval that's closed, because it gets 302.75 to 303 is a pretty tight interval, 0.25. And that uses only 32 bits per number by being flexible and growing up and down. You really can't beat that one uncertainty bit, but the designers say, it's variable size, can't stand variable size, can't keep track of it. We don't want to have a heap to manage the sizes. We don't want to expand it out to the maximum size. Just give a fixed size numbers. Okay, done. I heard you. Type 2 and type 3 are that way. Now with type 2 unums, I can craft the lattice to be really good for the decimal numbers, because like I say, you can customize the lattice to be whatever you want, just as long as you follow certain rules. And I can actually get 5 decimals of accuracy, 302.88, before it goes bad. But with posits, using an exponent size such that I have the same dynamic range, or actually bigger, 3 times 10 to the 144th power, no one can say that I cut down the dynamic range in order to get more accuracy bits. I've got both. I've got 6 decimals of accuracy, 302.882. But if you let me reduce the exponent size so I do get a little bit more accuracy, I still got a dynamic range of 10 to the 36th power on the bottom line. I've got 10 decimals of accuracy from a 32-bit number. That's like the maximum you can get out of a 32-bit number, even if it was an integer, right? I mean, 4 billion is an integer. That's a 10-digit number. So posits beat floats at both dynamic range and accuracy. And that's what I got out of just this formula. Of course, that's just one formula. Let's try solving ax equals b. And usually you'd probably do that with double precision numbers, but I'm going to use a really small system of only 10 equations. So I'm actually going to try to do that with 16-bit numbers. And it's exactly by the rules of LINPACK. If you know the rules of the top 500 scoring, they fill a matrix completely full of, it's a dense matrix with random entries between 0 and 1. Then they sum the rows and make that the right-hand side, so that nominally the correct answer is 1, 1, 1, 1, 1, 1, 1, 1. But you solve it by Gaussian elimination. You compare how close is your answer to just a series of ones. And that's how you know whether your computer system is working when you build a really big supercomputer, because usually the first time you run it, it's not a series of ones. It's something wildly wrong. But it's a good error check. But it's also become, of course, the thing that scores all the world's supercomputers, even though it doesn't really relate to any real applications anymore. It's not often you want a million by million system, all completely populated, not sparse. But I use the classic LAPACK method, which is LU factorization with partial pivoting. So I'm always picking the biggest element of every column to use as the pivot element. And you can see with IEEE 16-bit floats, dynamic range of 10 to the 12th, the root mean square error was 0.011. And I got 1.96 decimals of accuracy. I tried it with posits, I can do a whole bunch of these statistically. I just picked an example. The root mean square error is 0.0026, so it's 4 times better. And I got 2.58 decimals of accuracy. I call this beating floats at their own game. Floats are supposed to be good at some things like solving ax equals b. You do not want to try solving ax equals b with intervals. They blow up. And everybody does. They say, oh, I've got this interval arithmetic. Let's try using Gaussian elimination. Bad idea. It explodes. Now here is a totally unfair example that I picked out. I'm going to admit that it's unfair, but I did get it from somewhere else. It's from What Every Computer Scientist Should Know About Floating Point Arithmetic, which is a real classic by David Goldberg in Computing Surveys from 1991. Still worth reading. Very good explanation in a few pages of what you should know about floating point arithmetic. It's just like buckling concrete. You know, you're going to pop up the concrete by just very slight thermal expansion. And so these sides are only, the big side is 7, and these sides are 7 halves, 3.5, plus 2 to the minus 111th power. So I should be able to do this with quad precision floats, because quad precision floats have 113 bits of significance if you include the hidden bit. So I'll do it with 128-bit IEEE floats, and then I'll do it with 128-bit posits, just to show you that I can scale up to any size just like floats can. The answer that's correct to 36 decimals, at least as figured by Mathematica with extended precision, is as shown here. I don't expect you to remember that, but it's pretty easy to remember the 3.14 part, because by coincidence I landed on a pi-like number, times 10 to the minus 16th. So here's what you get with IEEE quad precision floats. 1 decimal correct. It's off by about 15%. And of course, as I say, there's no indication that it's off because you don't have any kind of U-bit to tell you, by the way, you really screwed up here and you don't know anything about the number past this first decimal. That's it's an awful lot of labor to produce just one decimal of accuracy. With 128-bit posits, in binary, it got exactly the same answer as you get from rounding the other one to 36 bits, 36 digits. So it landed on it, and if you wanted to do that with IEEE floats, you'd have to jump to octuple precision. I can shave down the size of a posit by any number of bits, and I found that when I got to 119 bits, I was still getting the right answer for this. 118, it starts to get shaky. But that's kind of the contest. It's 256 bits of float, 119 bits of posit. So you can see if you can save all that bandwidth, save all that memory, you're going to save energy and power, and the memory wall is going to be not so bad. You're going to make better use of those bits. So remember this from the beginning. The scalar product, A dot B, you always get this right in posits if you can represent those numbers. And to represent the numbers, 32 million and so on, all you need is 25-bit posits. The reason that 25 bits suffices is because fused operations are part of the posit definition. Fused multiply add is part of the definition. Fused dot product. In fused dot product, you do all the multiplies and place them where they would be, scaled appropriately. So you're doing like a great big sliding floating point accumulation. It may be 400 bits wide, 800 bits wide. But the amazing thing is, it's faster than if you round after every operation. 3 to 6 times faster. All it costs you is a few bits inside the CPU to accumulate as the accumulator. There is no reason in the world not to have a fused dot product. There was when it was patented, which the patent expired 2 years ago. Ulrich Kulisch over in Germany patented this thing and tried to get money for it. I think that prevented people from using the exact dot product, although IBM bought a license. But now that it's expired, it's high time to put it back into number systems, because now you can do matrix multiply with complete confidence and know you're within 1 unit in the last place after you do the rounding, because you only do 1 round at the very end. So if you have much less rounding, and it's 3 to 6 times faster. I've got the reference there. Bian Cullen and Jack Koenig at UC Berkeley have got the circuitry working for this. Then there's just not much of any reason not to use it. 800 bits on a chip is nothing these days, right? So in summary, posits beat floats at their own game, which is guessing their way through a calculation as best they can and minimizing the rounding error. It's better accuracy, it's better dynamic range, and it's better closure. I believe we are completely obsoleting floating point. I can't see a single reason to make a new chip that uses floating point when you could do this instead. Show me a place where floats don't do a worse job are harder to design, take up more space on the chip. I mean, they have absolutely no advantages. As long as there's been a trade-off, the float people have been able to defend, well, yeah, you're better at this, but I'm better at this, so let's just keep things the same. If you're uniformly better with a different method, and it does the same type of problems, and all you have to do is drop in the value, and it works exactly like a float did. You don't have to know anything about interval arithmetic or any of the other mathematics. All the same algorithms work, they just work better. Then I think it is time to replace IEEE floats with posits. So I wonder who's going to be the first person to produce a chip with posit arithmetic. I have a very strong suspicion it's somebody in this room. In fact, they're in the back row. They're already working on it. Rex Computing is here. And they've got their first silicon back, and they're testing it, but they're planning for a second batch of silicon that at least will offer the alternative of Unum arithmetic. So you can imagine a mode where it says, well, let's just do IEEE floats, or in this mode, use the posit type style. So I think that's going to give us the ability to pack more floating point units onto a chip. The GPU people are going to love that, right? Because they are taking up a significant amount of silicon just with their floating point multipliers and adders. So if I make their FPUs smaller and they can suddenly pack a bunch more into that real estate, they're going to really be interested. It could be like a 30%, maybe a 50% gain in the number of GPUs you can get. And I presume that the power consumption is going to go down as well because they're not having to do all this testing for NANDs and so on. Now at the end, my able assistant, Dr. Yonemoto, is going to try to do a live demonstration of these things using Julia. He's implemented them in Julia, which is a very fast but high-level language. He's even got an audio thing where we did an FFT, both with floats and with posits. So I hope he can get this to work.
All right, so let's give this a shot. So a couple things about this particular implementation. It's not backed by IEEE floating points. Everything is done as binary operations on 64-bit unsigned integers. So there are a couple places where I cheat and tell it that it's a signed integer, for example, to check signs, but the hardware doesn't really treat it any differently. Okay, so I don't know how many of you guys are familiar with the Julia programming language. If you ever do any sort of mathematical modeling and numerical modeling, it's a really great language for it. It lets you, and in particular what's important about this is, about Julia for this project is that it lets you redefine all of your, you create your own numerical types. They're first-class citizens, and you can basically plug them in anywhere you want. You can overload all of the operations in such a way that if there's a built-in algorithm to do something, you can usually, like for example, matrix multiplication was a big one. You can usually go directly and just immediately have matrix multiplication once you've implemented plus, minus, and multiplied. I think there's still. Did you guys got it going?
We reversed this, really, we did.
Let's try this. Let me, if I unplug and plug back in. Desk HDMI 2, I think it was. Oh, VJ2, sorry, VJ2.
Yeah. We're getting VJ2 to work.
Oh no.
We saw it, yeah.
Yeah.
Oh, there we go.
That's good. Good sign.
Thanks to the cycles.
Okay, and then we'll just move.
People don't ever want to see their displays.
All right, so this might be a little bit tricky because I'll have to do it this way. Okay, so let's fire up Julia. So I'm going to import the sigmoid number package, which is so all of this is open source on GitHub. So you should be able to get this if you also get Julia.
I made sure I was not under any kind of intellectual property agreements when I did all this, so I could give it away under the MIT open source license.
Right.
And we're sticking to that.
So first, we'll do what. So I'll create a type which corresponds to an 8-bit posit with one ES. Oops. And let's take a look at what the number 1 looks like in this representation. So you can see that the sign is 0, but this may be a little bit confusing because so it's legit 8 bits. It's secretly backed by a 64-bit integer in the system, but it will only tell you that there's 8 there. But if you want kind of a better description of what's going on, you can call it with a spacer, and what that'll do is it'll show you the sign bit, the unary regime bits, the ES, the exponent bits, and then the last 4 digits are the fraction. If you want to see something like 256, maybe that's too big. 16. For 8 bits. So let's do 16. You can see that the size of the regime has gone up. It's still a unary. It's a unary number that corresponds to 2 to the 3rd, or 2 to the 2 to the 2nd. Excuse me.
0 is a flag?
The 0. The first 0 is a sign.
The second 0. Yeah.
The second 0
That's
is
E size.
A flag.
It ends.
No.
Because
So okay. So let's do 32. That will turn that into a 1.
you always have to flip the bit, so it's R, not R.
So in this case, remember we're in the E size environment 1. So that means that for each of these unaries, the exponent goes up by 2. So in order to get to that exponent of 2 that's in between, say 2 and 8, or actually sorry, 1 and 4, or 4 and 8, you need to have another bit that turns on those exponents. Okay, so let's do some slightly more substantial.
You like a chair.
No, that's fine. Yeah. P1 of 3. So just to prove to you that this system can actually do some arithmetic, that works. We can also do an add, and we can also do a divide. Now, 8 bits is not very much resolution, so this will report as 0.59375, which is the closest representable value to 0.6, which is what you would expect. Let's do a slightly bigger system. Oh, thank you. And then we can do. Let's do the same thing as before, except do this in P2. And you can see it gets much closer. At the moment, I don't permit that. I want you to, this is kind of supposed to be like a hardware type emulation, and that's really discouraged.
Certainly languages could promote for you just like they do single precision to double.
All right, so if you want to take a look at what this looks like, let me add spacers. You can see that this is the representation of this number all broken up, and you can see that there's a long fraction bit with repeating decimals. It's currently rounding to nearest even, which is why the last one is a 0 instead of a 1, and it breaks the pattern of the repeating decimal. Okay, just for reference, we also have in this library we can also do this.
Do you have controlled rounding?
Controlled rounding.
No, there's only one rounding mode.
I have actually implemented more than one rounding mode because they're useful for the valids.
You need them for valids, but if you're going to do posits, there's only one rounding mode. You don't have to have 4 or 5 or 6 rounding modes.
Before you go on,
Yeah.
now the 32-bit number that ended in a 0, what would the value of that number be if it ended in a 1?
I'm sorry?
Would it be bigger by 2 to the...
The last 0
yeah.
there,
Okay. Let's do that.
1?
Oh no, it just rounded that value.
Yes, but what if you got a
Can
number
you
that had a 1
calculate
there?
Try converting 0.6000.
In other words, is it always 0?
No.
Oops. All right. Up. That should be farther from 0.6. I'm not going to do the math, but it's farther from 0.6 than the other one. Okay. Excellent. Okay, so let's do something maybe real.
You didn't convince me you made that last 0 a 1.
I'm sorry?
The very top of the screen.
It's 8 versus 9.
You were asking to make it 1 larger, you made it 1 smaller.
Yeah.
No, but I wanted to know if that very very last zero at the top of the
I
screen.
wanted it to be B, not A.
It'll be slightly larger than 0.6, and it'll be a little more than 0.6.
It's farther away.
It'll be another,
Because the one with the zero is 0.6000001.9. So
That'll make it farther away. Do you still want to see it?
Yeah, but when does it become 1?
when does it become
You said you always round, and that's what I was trying to
that's
understand.
only in the case of a tie.
Instead of previous.
Remember, rounded near even is only when it's an exact tie, and it has a choice between 0 and 1, it's halfway in between.
Oh, I'm
Then it will
sorry.
take-
Actually, in fact, this one isn't halfway in between. So round to near, you don't use the round to nearest even semantic at all. You just round it.
It's
And
not
it's
asking
right.
that question, it's asking what's next, instead of next of X. instead
Yeah,
of
can you
previous of X.
increment the binary by 1 and transform it back into a real? I don't know if you have that facility.
Yeah, that's what it just did.
Okay, there you go.
Okay.
Okay.
All right. All right. So let's do this. So I'm going to go into 32, 2, and I'm going to create a random array of numbers that are either 1, 0, or -1. If I can find my cursor. And make 65,536 of these numbers. Okay. And I'm now going to convert those into posits, 32, 2 posits. If you look at this, you find P array, P dot F array. And you can see that those are all posits that are either 1, 0, or -1. Let's do a fast Fourier transform on this array.
There's a lot of signal processing people that use 1, 0, or -1 for their signal. The seismic people do it, the radio astronomy people do it, but then they want to do it to 64 bits of precision.
So this is the fast Fourier transform of that random junk. I didn't actually program any complex numbers for Julia, for these number systems. I got them for free with Julia. And what I'm going to do next is I'm going to do this formula, and I'll go over this formula real briefly. What it does is it takes the complex difference between the result and what it started with, PRA,
So
right?
your
And the inverse Fourier transform of the Fourier transform array, and then it takes the complex distance of that difference, and then it sums it together. So you can see this is basically a net sum difference between it. And remember that number, it's 0.0022. Let's do the same thing with 32-bit floating points. And then I'm going to do the same thing here, except here I've already pre-done. I've done the Fourier transform and then done the inverse Fourier transform. And you can see that this is not as good. 0.01 instead of 0.022. 5 times bigger area. So one question is, does this have any real world implications? So I will go ahead and load a library from Julia. And what I'm going to do is the details of this aren't important, but I'm going to record some sound from the computer. Anyone want to give me a word to say real quick before I let this go? Okay, I'll do it in honor of Rex Computing since they're here. Rex Computing. Rex Computing. All right.
Was that transformed forward and back that we just heard?
No, that's just what I recorded to
Okay.
prove that I've done it.
Get a little clipping there.
So now I'm going to write this formula here and this function here, and basically, what just happened here? Okay. Oh.
This is a very brave demo, I must say.
Oh, hold on, sorry.
Oh no.
I accidentally didn't hit enter when I did that. So I'm going to copy the data so that I don't lose it first. And then I'm going to do this function here, which will basically take the function, do the Fourier transform, the inverse Fourier transform, return it back to float 32, and then output that as a result buffer.
And you're doing that with floats first?
No, this is I'm going to do this in, and note that it takes t, which is going to be a data type. So I can specify the data type when I call this function. Okay. So first I'm going to do it with 8-bit posits.
8-bit, yeah.
It's also going to output how far away it is, and the net difference is 169. And now we can listen to it. Rex computing. Not so bad. Now I'm going to also load up a custom library that I wrote called altfp. And what that is, it's an alternate small floating point library. This provides ability to custom generate floating points of varying sizes. In this case, I'm going to do small float 8, 3. So let's do this. Which means that it's an 8-bit float with only 3 bits of exponent. You're going to have to trust me that that's better than 4. And then you can see already that that there's a numerical difference, 180.925 instead of 169. So this is slightly worse. Also, this doesn't have nans, so I just let it, I'm doing the thing which we do with posits, make it a little bit more fair. And so this is what it sounds like. I don't know if you can hear the difference, because when I tried this, it was kind of in a noisy environment. But Rex computing. Yeah, maybe you can't really hear it. Mm-hmm. But nonetheless, for 8-bit encodings, it's not doing so poorly.
But you did get a superior sound difference in one of your experiments with posits. They sounded better.
It was actually the other way, but that's because I converted negative numbers wrong. Okay. All right. So the next. Anyway, so you can do fast Fourier transforms. They're more accurate using posits than they are using floating point or floating point style numbers. Okay, so the next thing I'm going to talk about is machine learning, which, as you might know, is a pretty hot thing right now. I apologize. This part might take a little bit of time. So a key thing that you can do with these is to do XOR the top bit and left shift. And I was going to do maybe some sort of like interactive thing where we try and figure out what that does, but I'm low on time. So let's just do it this way. So I'm going to show you that this in fact does what you expect it to do. So it's going to XOR the top bit and then left shift, right? So it XORed the top bit and left shifted 2. And then also let's see. Let's do one that's not negative. Oops. Got this problem. Bits.
That's the sigmoid function you need for deep learning. Imagine what it takes to compute that with a floating point call to a library to do e to minus x and of course a divide. With posits, it's you flip the first bit and shift to right 2 places, and you've got almost a perfect approximation of that function, which is why Isaac started calling them sigmoid numbers. They're just made, it's like they were tailor-made for neural networks. Okay, this I forgot to execute plot at the beginning to get this to run faster. So you can actually see this plot right here. So that's what this thing looks like. It has the same slope as the e to the 1 over 1 plus e to the minus x. So the natural question is, can you actually use this for machine learning? Okay, so and are there like advantages that you can take advantage of because of their nature? So I'm going to open up a library that I wrote called GenML, which is kind of a very early stage general machine learning package. And then here I'm going to define something, a 16-bit posit. I'm going to call it MLP. And what I'll do now is I will define this function, which it's going to be a Boolean function that takes a vector of 10 Boolean variables and then calculates a Boolean formula on it and then scrambles it 5% of the time. So this is kind of like, a really cheesy version of some sort of noisy data that you might use for machine learning.
So in this case, so the $sign is XOR. XOR is very important because it's not easy to do. It requires multiple layers in a neural net to get an XOR to work. So it's going to be V3 or V4 XOR with V1. Okay. And a couple of housekeeping things that I have to do. I'm going to assign in the monkey patch in the GenML library a couple of functions. So instead of a sigmoid, I'm going to use the pseudo logistic function, which is XOR top bit and left and right shift 2. Okay, and then a couple more things I'm going to do is I'm going to.
We had a hard stop at 5:45, but
Sorry.
Just the cameras go off. We have an internal session afterwards. You can tell us the juicy part.
we have
the room forever.
Okay.
Great.
So here I'm generating a 500 data set array of random bools, and then solving them through the noisy function to get a set of training results, and then setting up a training results array, and then solving the function f for those values, and then populating the training results. Okay. The next thing I'm going to do is I'm going to create a multi-layer perceptron that I'll call DemoNet, and note that this takes values everywhere. You can see this posit 16.0, which means it's acting on this 16-bit posit everywhere. So all the data in here is 16-bit posits. All right, so then I have this function to train with the result that I'm going to copy in. I'm just showing it to you so that you know I'm being honest and not doing anything sketchy. But this is what it looks like. It basically does 30 rounds of batch training with the entire data set as the batch, and then at the end it tests and outputs the percentage it got correct, based off of testing 50 random values. Okay, so let's do this. Let's see what happens. What happens when we train this guy? Okay, excellent. So it got 98% correct. I will generate a random Boolean array. And what was the formula? The formula was V1 XOR V3 or V4. So V3 or V4 is going to be false or true, which is going to be true, and then V1 is false, so that's going to be false XOR true, so the answer should be true. Unless this is in the 2% of errors, let's see what happens. Oops. Right, we need to convert that from not being a posit into being a Boolean.
this is almost like, which nut is
so
the
true.
bean under.
So it evaluated correctly. Good.
Oh,
I can breathe a little bit easier.
Like I say, this is a brave demo.
So I'm going to do this again, except instead of doing 16 bits, let's do it with 8 bits. And what do you think will happen?
Yeah, we won't get 98%, but you might get pretty good.
Okay, so now this is the same thing except with 8-bit posits. All right. So if I actually go ahead and train this, it's going to get me no better than random.
Yeah,
Okay, so that's a problem.
that's too small.
Okay, so how can we fix this problem? Well, maybe we can do it by increasing the bit size. So something catastrophic happens between 16 bits and 8 bits that makes this not work anymore. All right. Unfortunately, I have to exit Julia and bring it back up because otherwise it will not know that I'm handle what I'm about to do well. So I'm going to do all the same things. I'm going to redefine all the things that I just defined. So basically, I've redefined f. I've imported all the libraries, assigned the sigmoid values, generated the input matrix and the training results, and then this time I've set it to 8.0, just like before. And then I've created the new demo net and populated with random variables. Oh, where did I mess up?
Darn. Why don't you just tell us how many bits it takes?
Okay.
We'll trust you.
Right. So the key point is that all you have to do is monkey patch the outer product, and let the outer product be a 16-bit outer product, and then magically everything works. Just one function in the process.
Great.
And yeah. So when you do that, it's able to train correctly.
Fantastic. So if you could use 8 bits instead of 16 bits, you could go twice as fast as even these special purpose hardware things that they're building to do.
Oh, I see where
training.
the problem is. So.
How do you figure out what you
That was by trial and error, and the way that I did it was first I did it with the 16-bit posits, and then at every stage of the machine learning process, I constricted the 16-bit posits and trimmed them down to 8 bits, and then I found the one place that was critical. And then I did the inverse experiment, which is to take 8-bit posits and then see if I just expanded to 16-bit posits in that one place. It's trivial, right? The representation is identical. So internally, Julia doesn't know it's treating everything as a 64-bit int under the hood, but it just doesn't truncate and round.
Yeah.
So the interesting thing is that this could be a way to make machine learning much more efficient. So actually, if I
think
could,
one of the first places these things might show up is in GPUs, because as long as it's putting the right pixels on the screen, no one cares what the format is, to a large extent. I tried to get AMD interested in it, but that was before AMD finally had some cash on hand and they couldn't do anything. So maybe we can
so
try to do
actually,
that now.
I'm pretty sure this will work. So here's monkey patching the that one function. You can see I've added these widen directives here, which will widen the values at this one place where it's doing the matrix multiplication. Okay. And then, so it gives me warnings because I'm monkey patching a function. And then if we train this, now remember, everything's still 8 bits, 90%.
Not bad. Yeah, maybe acceptable. All right, I think that concludes our talk.
Sorry to go over here.
Thank you, Isaac. So now we can do questions and discussion, and you can tell me why this will never work, which is, yes.
Dennis, he's going to put your slides up within an hour.
Great. I thought he distributed them ahead of time so people could follow along.
No, it'll be on the website now.
Okay, good. Yes.
So I have several algorithms that require that I be able to control the rounding direction. Because if I don't, then the min could cross the max, and then they don't work. So that's a significant thing.
Min could cross. Well, I think as soon as you start getting into things like that, that says you need valids, not floats. In other words, don't use posits, use valids. There's all this machinery for doing wonderful calculations and that's all developed, like I say.
The other thing is I've successfully used the overflow and underflow sticky bits to run the fast algorithm, check the bit, and only if it had an overflow and underflow rerun with the slow algorithm. I've done that.
And I'm a big believer in that kind of runtime control as well.
And I've used NANDs to avoid exceptions in the middle of expensive calculations.
Yeah, I think we do need a way that you can keep on going. Let's say you're doing just a whole list of calculations and only one of them is bad. You want some way of being able to continue to proceed, throwing out that one
So I'm not
answer.
about the number format, but there are features in the IEEE that are there for a good reason.
Yes, I just don't want to keep feeding a NAND as an input into a floating point unit, if possible. Yeah.
Conventional rounding in fast Fourier transform introduces a bias. Do you have a way of changing that to say random rounding?
Which is how is it biased? If you're, let's see, if you're, is your signal has a DC level?
Yes.
Oh, yeah, we've run into that. Let's see, that's a tough question. I was using experiments where there was no DC level, and I wasn't running into it.
Okay.
So if you're rounding, you're saying round to nearest even introduces a bias.
I'm just saying rounding, the conventional rounding introduces a bias which can be eliminated by doing random rounding, up or down.
Instead of round to nearest even.
It adds to the noise being preceded.
Yeah, that's a tough one. I'll have to think that one through. Yes?
You said that posits can be used as a drop-in for floating point. And I'm trying to understand what that means, because if I wrote a floating point library, and I had to pay attention to all, have to add logic for all the underflows and overflows and nands and so on, so that software won't work exactly with posits. What do you mean by
won't get
drop-in?
any nands, you won't get any overflows, you won't get any underflows, and your answer will be more accurate. In that sense, it's a drop-in. So all the exceptions you put in to handle bad things.
Binary code will have to be.
The only thing that could go wrong is if you say if number bigger than 2 to the whatever, and you've got some magic numbers where you want to let's say truncate to 0, then those would probably have to be changed if you've hardwired things into your function. And I know, let's say if you've got a routine for computing cosine of x and you've got the polynomial coefficients laid out, I think you'd probably want different polynomial coefficients for approximating cosine if you had posits than if you wanted floats. But in general, there's nothing to do with interval arithmetic, where you would have to do tiling methods or watch for expansion and things like that. That's what I'm saying, is the same algorithms would work.
So, as I showed in my demo, when I did the fast Fourier transform with 32 bits floats versus 32 bit posits, that did not branch off into two different
Yeah.
But you probably had no logic in there for floating point anomalies anyway.
The process was identical. The thing that the computer, I mean, obviously to actually do the adds, subtracts, and multiplies, there were different mechanics.
There's no problem, right?
Right,
Yeah.
but like the actual outer algorithm was identical.
If you wanted to convert the NAG library over, it wouldn't be that hard to convert it to posits. It'd be, if anything, you'd take code out because you wouldn't need it anymore, and it would just get, yeah.
The error you reported for the fast Fourier transform comparison sort of brushed over what could have been some serious spotty errors. Did you make any calculations to show the maximum error in the two different calculations?
That's a very good point. I just finished the fast Fourier transform yesterday, so
Right.
not yet.
Yeah, you do experiments first, and you follow the more
edge.
theoretical underpinnings and try to figure out, well, is this just luck, or is this always going to happen? And then you get some proofs as to what's the worst thing that can happen. We haven't done that yet.
So when you talked about the IEEE floating point giving different answers on different machines.
Yes.
Was that using multiply, add, and double extended, or was that just the straight standard?
One of the first places that happens is if one uses fuse, multiply, add, and the other one doesn't, for
Yes.
example. But if one has an 80-bit accumulator, let's say because it's got 87, and the other one does not, then
Okay.
you've got problems
Well,
there.
that's why the standard didn't include the 80-bit in the registers. And multiply, add is actually not allowed by the standard.
Unless you call it a multiply, add.
Well,
You see, the thing that you do in Posit Arithmetic, the compiler in Posit Arithmetic should not be allowed to replace a multiply and an add by a multiply add without explicit permission by the user, and it's a different function. Just as fuse dot product is a different function.
but the IEEE standard itself doesn't include it, and that's just an add-on.
That's just it. There's a whole lot of things in the IEEE standard where they were not thinking about making bitwise compatibility, and you can add them on and fix that. Yes.
My question was going to be the same thing. This may be a semantic issue, so that doesn't apply. But it sounds like what you're saying, if you do things that are beyond the scope of the original IEEE standard and get results that the original IEEE standard wouldn't allow you to get, those results might not be the same. I mean, to the if you were not allowed to extend the standard to do things like the fuse, multiply, add, would it still give you potentially different results on different machines, or are those differences because the machines took liberties with the standard?
Why is this? Okay, the reason the standard gives differences is because it has options as to what you must do and what you might want to do.
Okay, that's what I want.
Belkahan runs his algorithms without any of the options.
I
run him with all the options.
But he was interested in letting people improve the results any way they can. So if one processor said, "Can I use a couple of guard bits here and keep them through all the calculation and only round when I hit the equal sign?" He said, "Yeah, it'll give better answers." But every user I know is really upset when they get a different answer and they don't know which one is the better answer. They just know they're different. And is it a bug? Is it a rounding error? Pain. Yeah. Yeah.
The reason I was queuing in on that is one of the early Intel microprocessors that implemented the fused multiply add was the i860 machine.
Oh yeah, I remember it.
89 timeframe.
Yep.
And there are people who have said that one reason that didn't succeed better is because they took this particular liberty with the floating point standard, and thus people did not get the same results. And whether that was an issue or not, or whether it was an improvement or not, the fact that it was different was a target that people could throw at them.
Right.
Here, multiply these numbers, and you'll see that it didn't work right.
You might also remember the early days of the C language. When it was first introduced, the rule was that as you entered a routine with floats, they were automatically promoted to doubles. And people said, how do we turn that off? Because they did not want it happening without their control. If they wanted doubles, they were going to ask for doubles. But it's going to be so much better. You're going to get double precision. It'll be great. No, they don't. Stop helping. Stop helping. We'll do it. If we want it, we'll do it.
IBM had the same issue on the 360 series with the 36091. To get a pipeline divide, they actually did worse rounding sometimes, a very small percentage of the times. And it meant the nuclear industry couldn't buy that machine.
Yeah.
But the scientific computing people were very happy because pipeline divides ran quite fast.
Yeah.
Well, partial accumulation was a quick way of saving memory for a lot of stuff.
Yeah.
But you had good arguments on your first two arguments at the beginning to do this. There's actually a third problem, which is in the ACM undergraduate curriculum. The curriculum has only 1/4 for numerical methods.
I'm surprised there's that.
Yeah, no,
In
actually,
almost any university in the country, in the world, you can get a degree in computer science without ever touching numerical analysis.
that's right. And actually, a lot of that has to do with complaints by students who find discussions about floating point like this exceedingly boring. I had a 3/4 numerical methods class myself. And
Well, when I teach parallel processing, I teach them with things that round, and I right in their face, they get different answers when they group things in parallel instead of doing them serially from left to right. And they usually do not get taught that in most universities because it's an ugly example.
so I think you need a third slide basically saying we have to change the thinking in a lot of CS departments.
Well, maybe. I mean, when I debated Kahn last July, he's of the opinion that the whole world has to change so that we go back to analyzing every single line of code for its rounding error. All 10 million lines of code that you've got, you have to analyze every single one. And everybody's a bad person if they don't do that. I don't think it's going to happen. I think even fewer people are doing numerical analysis now than there were 10 years ago, even fewer than 20 years ago, and we have to find ways to make it more automatic and higher quality.
There is a difference between numerical analysis and numerical methods.
Yeah.
When I taught numerical methods, I didn't teach why the algorithms would fail. I taught them how to figure out when the algorithms would fail. But not do the proofs, but just by a simpler analysis.
Like turn down the precision until it fails or something like that.
You don't have to go that far. But So numerical analysis is a very mathematical discipline.
Yes.
Numerical methods can be taught as a more engineering approach.
Right. I completely agree. And you might be able to get away with teaching that and getting some more literacy in that. But there aren't that many numerical analysts out there. Yes.
Getting away from the technology and theory, what's driving you to do this? Your love of numbers, or is there some business opportunity here?
I'm not doing it for the money, that's for sure. I mean, that's why I'm giving it all away. Although I'm discovering I'm making more money on consulting than I ever would do probably if I were trying to charge license or royalty fees. So if you're trying to introduce a new number system, you don't fine people for using it, right? They're never going to touch it. But I think my royalties on this have been almost $1 an hour now for minimum wage price. So, because yeah.
Well, I'm going to tell Dave Bailey, he needs to look at what you just presented. If you haven't talked to Dave already.
Well, Dave Bailey was one of the reviewers of the book.
Yeah. So and also one of my other former coworkers who used to do a lot of CFD, and there's communities that appreciate this. The CS community tends to appreciate it less, though.
So what really motivated me mainly was at Intel we were trying to get to exascale computing, and I was leading the research group trying to drive that. And we quickly identified that the pathway between DRAM and processor was going to use 100 megawatts all by itself. And we're limited to 20 megawatts for an exascale supercomputer. So if you can't get that down by technology trends, just saying, well, memory's getting lower power, because it wasn't. The trends were not going to get it down below 100 megawatts in the foreseeable future. Use fewer bits, make them more meaningful. And it might cost you more transistors on chip, I said. You might make a much more complicated FPU, but it'll pay. You could maybe use 3 times as many transistors on the FPU, but make every bit count, and you'd win because you'd be moving far fewer bits, and you'd be able to get away with single precision instead of double precision everywhere. We throw 64-bit precision at everything these days, and that's one thing that's stopping us getting to exascale. So that's what really motivated me was trying to get past the memory wall problem. But I'm always attracted to a problem where I see there's a better solution, but everybody's doing it this way because that's the way we've always done it. And that was the way with parallel processing in the 80s. We could see that parallel processing was a great thing, but hey, you know, you have to change all your code, and it's already written and optimized for these vector machines, and it's not going to happen. But it did happen. I love to see those revolutions where it just goes to the breaking point and suddenly, poof, everybody's doing it in the new way.
So what are the difference between the original Unums and Posits is that the Posits are array friendly because you pick a fixed size for them. What about the number of cycles to do, say, a multiplier divide? Is that now constant?
Yeah.
Among all
Yeah.
Posits?
Just like it is with floats.
So it's also kind of GPU friendly then as well?
Very GPU friendly, very Rex friendly. They've got a VLIW, and then you know exactly how many clock cycles everything takes. So yeah, you don't have, and the lack of exception handling should help you. You have just 2 exception numbers, 0 and plus or minus infinity. Those are the only 2 you have to watch out for, and you do those off to the side while you're going ahead. The only thing I would caveat it with is my multiplier is going to be slightly bigger because I get a little bit more precision. So like in a double precision number, 64 bits, 61 of them might be the fraction if you have an ES of 0. So you might need a 122-bit multiplier in order to be able to round correctly. And that's a little bit bigger than the 106-bit multiplier that you need right now. But I'm pretty sure that's not going to swell the silicon area of the FPU by that much. You've got a lot of other logic that you've got to worry about in an FPU.
Taking exceptions out.
Yeah, taking exceptions out is a very helpful thing.
You guys should have dinner with John now. I'm on Stanford, so
Let's go dinner.
let's do it.
All right, let's do dinner. Thanks very much.